All right, hello, here we go with our online lessons. So this is the first time I've ever done this, so hopefully this is helpful for you. If I'm going too slow, you can always play it at double time. If I'm going too fast, you can always pause it. So we left off in lesson 4 with example 5. Find the area of one of the regions bounded by the sine and cosine curves. So when you think about sine and cosine, sine is this one down here that starts at 0, 0. Cosine is the one that starts up at 1. If I make these two different colors, just so they're easier to see, we can see that sine's going like this, and cosine is starting up at 1, going like this. And they want us to find just one region that's bounded by them. Notice there are two different regions. We're just going to use the first one. It will be shorter, easier values of x to use. If you notice, we're going to let f of x be sine x. And we'll let g of x be cosine x. And if we look at the region here, the first region here, if you notice, I always have sine on top of cosine. So since we always have one function that's on top, we are going to be using those vertical rectangles, which means we're going to be doing this with respect to x. So I don't have to change anything about my equations. We're good. We can work with them just as they are. To find the bounds, where I'm starting and stopping here, I know it's this point here and it's this point here. To find exactly what those are, since I can't tell by looking at the scale, I need to set those two equations equal to each other. When are sine and cosine equal? Well, if you look at your unit circle, that happens at pi over 4, and then again at 5 pi over 4. This would be a great opportunity while you have all this time off from school to really work on memorizing that unit circle. Maybe you could just try to recreate it, maybe look at it maybe 3 times a week and try to recreate those major angles that are happening on it. Awesome, so we found the bounds. Now we want to integrate to find this shaded region in here. Remember, we're using vertical rectangles. So my area is going to be the integral from pi over 4 to 5 pi over 4. And since sine is the one that's on top, that's the one that goes first. So we're going to have sine x minus cosine x dx. When we integrate that, sine is going to become negative cosine, and cosine is going to become sine, and our bounds are going to stay the same. We didn't have to use any u substitution, so the bounds just stay the same. All right. When I plug that in, I'm going to get negative cosine of 5 pi over 4 minus sine of 5 pi over 4. Okay, so that's like our first group, and then we are subtracting off the second group, which would be cosine, negative cosine of pi over 4 minus sine of pi over 4. All right, and that will become, since that's where they're equal, that's square root of 2 over 2. We're going to get plus square root of 2 over 2 for the first one, plus we get square root of 2 over 2. Hey, there's a sound you probably aren't hearing right now. Bell just rang. Okay, so when we work all those out, we're going to get 2 times the square root of 2 over 2. If you weren't sure what happened in there, you can always pause it and go back and look at it. All right, cool. Moving on to example 6. This one is a little bit longer. Make sure it's showing up in your screen. There we are. We're going back to area as an accumulation process, revisiting that idea. The graph of the function g consists of a quarter circle, you can see that here, and 3 line segments shown at the right. Let f be the function divided by f of x equals the integral from -1 to x of g of t dt. So they want us to find f of negative 5, so that means we need to find the area under the curve all the way back to negative 5. So for question A, let me make sure you can see that. All right. So f of negative 5 is equal to the integral from negative 1 to negative 5 of g of t dt. All right, notice that our bounds are flipped. My lower bounds is on top, so to change that, we're just going to do the opposite sign of the same integral. That's one of those integral properties that we talked about. All right, and if I look at my graph here and I find my area under the curve, you can see that from negative 5 to 3, I can find that one, because that's the quarter circle. And then I'm going to add it with the triangles that then go from negative 3 to negative 1. And splitting them up like this sometimes just makes it easier to see and make sure that we're less likely to make a mistake. If you notice here, with these triangles, this triangle is exactly the same as this triangle, and since they're both to the left of our starting point of our accumulation function, that means this one would be positive and this one would be negative. But since they're the same size and they're the opposite sign, they're just going to cancel each other out. So really, I'm just left with the area of this quarter circle right here. And since our radius is 2, we're going to have 4 pi. And then since it's a quarter circle, we're going to divide that by 4, which means I'm going to be left with just pi and 0, which means my final answer is pi. So f of negative 5 equals pi. That's a nice review. Part B, find all the values of x on the open interval from negative 5 to 4 where f is decreasing. Justify your answer. So pause for a second and think about where is it going to be negative. It's going to be negative where this is our derivative, and where the derivative is below the x-axis, that's going to tell us that the original function is decreasing. So f is decreasing on the interval from negative 2 to 1, since f prime is 0 and f prime is the graph that they gave us here. So the graph of the function g, right? So g, we need to make this connection that g of t is equal to f prime of x. All right, so we're showing the notation connection that this graph, g of t, is the derivative of our function f of x. And so if this is negative, then we know that f of x is decreasing. Part C, write an equation for the line tangent to the graph of f at x equals 1. I encourage you to pause right now and find that yourself, and then hit play to see if you got the correct answer there. So where x equals negative 1, my slope is going to be negative 2. Right, because g of t, g of negative 1 is negative 2. So that's how I know my slope is. My equation is going to be y equals negative 2, and then we have x minus the x value, which is negative 1, so that's the same as x plus 1. And then our y value is the accumulation function at negative 1, and if you notice, we're going from negative 1 to x, so if x is negative 1, my bounds are the same, which means my rectangle here has a width of 0, which means this would be plus 0, and I don't need to write that. I can just leave it as y equals negative 2 times x plus 1. Letter D. Find the minimum value on f on the closed interval from negative 5 to 4 Notice they said closed interval, so that means I also need to check the endpoints, right? So go ahead and find all the places that you think you need to check. Pause this, and when you come back, we'll check and see how you did. So we need to check where the derivative is 0. Right, so that's where g of t equals 0. All right, and we also need to check endpoints. Don't forget about the endpoints because it's a closed interval, right? So we're checking where the derivative is changing from negative to positive. All right, so all the places that we have that happening, that's happening when it's changing from negative to positive at x equals 1. So we want to check where x is 1. But we also want to check our endpoints. So I want to check what's happening at -5 and 4. So again, don't forget to check your endpoints. And what we want to know is what they have accumulated from there, keeping in mind our accumulation function is not starting at 0, it's starting at -1. So find the area under the curve, and you'll find out that this one is -pi, this one is -2, and this one is -1/2. So we're going to have the minimum value is occurring here at -pi. That's the lowest f of x value. So the minimum, can you see that? Okay, you can't. Minimum occurs, oops, forgot the R, occurs at x equals -5 and is -pi. All right, last example. Example 7, and notice it says we need to use a calculator. If you don't have a graphing calculator at home, which most of you do not, feel free to use Desmos on your phone. The app is free, and you don't have to be connected to the internet after you've downloaded it to use it. That's my favorite part. All right, the density of cars on a 10 miles of highway approaching Disney World is approximated by f of x equals 180 times 4 minus the natural log of 2x plus 3. X is the distance in miles from the Magic Kingdom entrance. Find the total number of cars on this 10-mile stretch. So again, this is accumulation function. If we're looking for accumulation, we are looking at using this function and integrating it. Our bounds would be the 10-mile stretch, so from 0 miles away to 10 miles away, and then we're going to integrate this function here. And all you got to do is type that into your calculator. If you don't know how to do accumulations on Desmos, I will show you real quick. When I open Desmos, okay, there's some glare. Hopefully that's better. If you click down here where it says functions, and then go to miscellaneous, notice the integral one is all the way down here on the bottom left. You need to type in your bounds. And then we're going to type in the function. Natural log is also under functions. Oops, I forgot the 4 minus. 4 minus. All right, 2x plus 3. And notice it doesn't give you anything until you go outside of this and type in dx. It is very unhappy if you don't give it what you're integrating with respect to. Okay, and then you can see your answer down there. So if you don't have access to a graphing calculator, you can use Desmos. And that are all of the examples from this lesson. Please make sure that you go and do the homework from this section. There are your answers that you already have this sheet for that. So please check your answers, and if you have questions, you can email me. And I will try to be really good about checking my email in the next coming 3 weeks.